The main theorem. What is main theorem? Main theorem is this. Let x and omega is a symplectic variety defined as a complete intersection. So of homogeneous polynomial f1 to fr, and omega is homogeneous with respect to the natural sister action, scalar action on x. It's then, and I assume that this is a symplectic variety, but singular. This is a singular symplectic variety. Then the main theorem says this x omega is isomorphic to some nilpotent variety of complex semisimple Lie algebra together with constant Kirillov form, and n is some, yes. So I want to prove this. So now these polynomials are homogeneous, so we put its degree, let ai be the degree of each defined polynomials, and by the definition of singularities, we may assume degree are all greater than 1 is for any I. Because if there is some linear form, then you can eliminate one coordinates by the equations, and everything can be reduced to this case. So we may assume that each degree of the polynomial is greater than 1. So now first I prove the following, the lemma. The weight is this is just TL omega. This is the sister action, and if you pull back the sister action, then it becomes TL times omega, and this L is the weight. Usually this is a integer, but in our case the weight should be 1, and the sum of AI should be n plus r. This is the lemma. How to prove this? So omega is symplectic form. So, and the dimension is 2n, and this is so let us consider omega n. This is nothing but omega wedge n times wedge of omega. But this is a canonical form, holomorphic volume form. So by using residue formula, because it is a complete intersection, the residue formula, it is written as the following: dz1 to the coordinate is z1 to the n plus r. So 2n plus r, and so the residue, she times the residue. Here, she is nowhere vanishing function, but this is pure weight, and this is also has pure weight, so it has pure weight, and so this is homogeneous, nowhere vanishing homogeneous function on x. But such function should be constant, because if the degree degree is greater than 0, degree is positive, strictly positive, then it should vanish on the divisor, on some divisor on x. So she should be constant because of nowhere vanishing. So this is actually this is a constant. So this is a constant. Yes. So let's compare the degree of each side. What is the degree? Degree is nothing but the degree, the weight, degree, or weight, anything. The weight and degree are the same. So the weight omega n is nothing but n times weight. This is n times weight omega, the degree. And what is the degree of this? This is the degree 0, and this is degree 1, 1, 1, 1, and so this is the 2n plus r minus. This is each degree is this. So we have the following inequality. R. But here, each AI is greater than 1, so this means that the AI is not less than 2. So this is the 2n plus r minus 2r. Yes, 2r, yes. And so this is the minus r. But r should be strictly positive. Then it becomes 2n. Yes. And on the other hand, x is a symplectic variety. So x, this means that symplectic. So the definition of symplectic variety says that the holomorphic form extends to holomorphic symplectic form extends to a holomorphic 2 form on resolution. It guarantees that omega weight of omega should be positive. One can check this. I will omit this part, but anyway, this is positive, so it has mild singularities. So this guarantee that this weight is positive. So this is the positive. So this is of course 0, and this is an integer. So omega weight of omega is should be 1. And if this is 1, then this is n, and this is n. Yes. So this is n. So this is n plus r. So this is n plus r. This is the proof. And okay, now let's start the proof.
So here, for every n, such a singular symplectic variety is possible?
Not possible, because as a conclusion, this is always nilpotent varieties. So we can classify it. We know all nilpotent varieties because we know all semisimple algebra. So you can calculate this dimension, and so the dimension is nothing but 2n. So maybe not all, but it is. You can calculate every dimension of n, because if you if you are given a complex semi-simple real algebra, then it's easily calculates the dimension of this. Yes. So let's start. So let's start from X. Then this is of course conical symplectic variety in the last lecture. Yes. What is a conical? Conical symplectic variety is nothing but a fine symplectic variety which is graded positively. But of course this has a sister action, and this sister action has only positive grading, so it is conical symplectic variety. So in the last lecture I proved that if X is a conical symplectic variety and X has complete intersection singularities, then X always has a Crepant resolution. So we get the Crepant resolution. Crepant resolution. And moreover, this Crepant resolution, one can take this Crepant resolution so that this is a sister equivariant. So Y has also sister action, and this is sister equivariant. And so this Crepant resolution induces the following map. And one can model out, one can take quotient of these things by sister action. Minus sister action. Then one can this. But this is a fine cone, so this is nothing but px, projectivized cone. And we put this z. Then we have a natural map from z to pi. We call it pi bar. Now we have a following situation like this. But we pi bar. Here, an important thing is that this is a sister bundle because the action of sister on X, each coordinate has weight 1, so it is a sister bundle in a usual sense. But if the weight if you have some weights are different, then usually it is not sister bundle, just multiple fiber occurs. But in our case, we are lucky because every degree weight of coordinates are 1, so this is a sister bundle. And one can check that this is just a fiber product of this is a fiber product of this diagram, and this is also sister bundle. And this is a Crepant resolution. This is smooth, and so this is also smooth. And moreover, one can check this, that this is Crepant, so this is also Crepant. So we have a following proposition. This induced map is Crepant. Is also a Crepant resolution. But now X is fine. But now this is a projective. This is projective variety. Of course, it has a singularities. But anyway, this projective variety has Crepant resolution. So this is a projective manifold. So now we come to the projective category, and one can use many techniques in projective geometry and things. Now, X has a symplectic structure in some sense, so Px should have a contact structure, and Z would have a contact structure. I want to explain this more in detail. Here we use the contact geometry. And here you have a natural map from Px to Px and restrict it to the regular locus of this variety. Then the restriction of this C star bundle is not this C star bundle is nothing but the regular part of X. And of course, this is the canonical projection. It is naturally identified with this is naturally identified with all X minus 1. Sorry, this is nothing but the OPX minus 1 times. This is the dual bundle of tautological dual line bundle, and the times means that this is a line bundle, but times means that C star bundle obtained from this by excluding the 0 sections. So this is the just the Px reg minus 1. This is just the restriction of this bundle. Sorry, this is the times. This is a C star bundle. This is C star bundle. Okay, the situation is this. Now we have a familiar situation. Here you have omega. Omega is a symplectic 2 form, and the weight is just 1. Weight is just 1. Then, by the, I think, first or second lecture, this symplectic structure gives a contact structure here. So this is a compact structure, and this can be regarded as the twisted 1 form. So twisting is just if the weight is 1, so the twisting just write this. Twisting is the OPX leg 1. Yes, this is the contact line bundle for this contact structure. Anyway, the regular part of Px has a contact structure. And contact structure means that this this volume form is non-degenerate. Is nowhere vanishing. Kpx reg plus OPX reg n. This yes, this means that contact structure means that it is equivalent to that. This is nowhere vanishing. This is a line bundle, and so this is a trivial because of this nowhere vanishing section. So this is nowhere vanishing. But actually, this contact structure can be extended to contact structure on Z. I want to explain a little bit in detail, because this is nothing but this. If you put let I be the natural inclusion of the regular part. This is natural inclusion. Then this is, of course, as a by definition, this is this leg plus OPX1. And the projection formula together with definition of I star. But we have following property: I star omega px reg is isomorphic to pi star omega z1. And this is for example, this comes from, this has a log terminal singularity, and this is this always holds by the result of Quebec's sorry, Quebec's Pitanel or some some peoples. So this means that such a form can be extended to the one form on Z. So this means that the one form on the regular part can be extended to the holomorphic one form on wall Z. This is the meaning. So we have this is the Z pi px pi bar Z. Of course, this is times p x1, and this is the nothing but Z omega plus times pi star OPX 1. Yes, this is natural identification. So this one form is originally, this is a twisted one form on the regular part of px leg, but by using this identification, this theta can be regarded as the twisted one form on Z. The twisted line bundle is twisted line bundle change here, but this is the meaning of this identification is just a pullback of this theta and extend. So theta can be regarded as such a form. On the other hand, this part also can be regarded as I omit some part, but anyway, we can get some. We have a following identification. So and so this is this is nothing but the pullback. Sorry, maybe it's better to write down more precisely. This is kpx times opx, and this is the z, and the pullback of it pi star kz plus pi star opx n. This bundle is nothing but a pullback of this bundle by pi bar, and if this is nowhere vanishing here, this is also nowhere vanishing here, because there are the difference is just some codimension 2 part. So this is nowhere vanishing here, and this is nowhere vanishing here. But this is a pullback of this bundle, so this is nowhere vanishing here. Yeah. So as a twisted one form, this is nowhere vanishing on this vector, on this line bundle. So this means that theta gives contact structure, because if this is nowhere vanishing, then this such a twisted one form gives contact structure, as I explained in the first lecture. So this gives a contact structure on Z. So now we have a following proposition. Z is a contact projective manifold. Okay, so now, but we are in a situation to apply the structure theorem of such a projective contact manifold. Let us recall I must divide two parts. I will explain. I should explain before, but I will explain now. So the situation is x omega inside here, and then we have following. But the case n is 1, and we divided two cases. If n is 1, then this is the AI, so this should be, this should be, this, if n is 1, this is 1, so we have a following, R is 1 plus R, yes. But each AI is strictly positive, not less than 2. So this is 2R, yes. And this means that R should be 1, yes. So in this case, X is just a hypersurface because R is 1 by this. So in this case, X is just a C3, and one can check that this is just a hypersurface defined by homogeneous polynomial, and it should be rational Gorenstein. So this is just a quadratic. The linear form is not permitted now. So this is isomorphic to by after some coordinate change. This is just something like that. Then in this case, this is the nilpotent variety. This is a nilpotent variety for SL2. See, it is easily checked. So from now on, we assume. So we assume from now on, n is greater. Okay, so now let's go back to this situation. So Z is a contact projective manifold, but the structure theorem of Quebecus, Peter Nelson Mays, Wisniewski says that the following: Z is, let us recall, this is a projective contact manifold, and KZ is not nef. Then one of the following occurred. Following. The case A is the Z is a Fano manifold with B2 1, and the second case is Z is just a projectivized cotangent bundle for some projective manifold M, and contact structure with contact natural contact structure. What does it mean? Natural. Natural means that the T star M admits a canonical symplectic form, and it induces the contact structure on the projectivized one, as I explained. And contact line bundle is just a tautological one. Okay, so I want to explain. I want to apply this, but this is a resolution of singularities. But in our case, we assume n is greater than 1. So this means that Px has singularities. because X is a complete intersection. So by Bouville's theorem, the codimension of the singular locus is just 2 in this case, together with Kaledin's result. If X is singular, then the singular locus has codimension just 2. So in this case, Px also has singularities. So has actual singularity. But in this case, this is not so, because this is only yes, the origin is only the singularities, but the px should be just a P1, and in such a case, Px is not smooth, but in this case, this has a singularities. So this has a singularities. So, and this is a resolution. So you have some. This is a projective birational morphism, and there is some exception locus. So the Betti number is, of course, this is a projective variety. So the Betti number of Z should be bigger than 1. So this case doesn't occur. So this case occurs. So by applying this theorem, KPSW, Z should be some sort of things. And moreover, this by the construction, this Z has a contact structure, but its contact line bundle is I erased here. I wrote down here something like this. The contact line bundle is contact line bundle is just star OPX1. So, but here the contact structure should be natural one. So these contact structures should agree. And so this agreed. So the contact line bundle is just this. This should be agree. This should agree. PX1. And this is a contact line bundle. Contact line bundle. Okay, so, but what is M in this case? So the next question is, what is this M? Of course, this is a 2n dimensional, and so this is the 2n minus 1. Yes, because this has 2n, so this has 2n minus 1, so this is 2n minus 1, so this is 2n minus 1. So M is the dimension n. Yes. So what is M? So the next proposition says that this M is actually flag variety. So M is written as the following: G is some complex, semisimple group, and P is a parabolic group. So here the Lie group appear and the gay, so the gay appear. So the main results say that if we start with such an assumption, we get some nilpotent variety for some Lie algebra. The Lie algebra here appear. G, yes. So here G is nothing but actually odd M. In this case, the neutral component of the automorphism group of M. Actually, so I want to prove this. Why this is true? Because this means that M is a homogeneous variety. So homogeneous variety is nothing but manifold whose automorphism acts on that variety transitively. So we we first check that the automorphism group of M acts on M transitively. So this is the first part. But here we have a following good condition, because this is a tautological bundle, but the tautological line bundle is pullback of something. But this is very ample. So this is a base point free. So this is base point free. So, but anyway, so by using this, this is a base point free. So by our assumption, we know this P T star M P T star M 1 OP this is the surjective. So we get this as condition from here. But now I want to prove the following. The M, there is a natural map here, theta M. This is surjective. Yes. There is a natural map, because if you take a global section, then it's you can this is a natural map. And if this is surjective, then automorphism group. If this is proved, then automorphism group. Then if this is true, then the automorphism group, the neutral component, acts on M transitively. If this is checked, then this is transitive. So then we get the following form. So I want to prove this surjection from this assumption. This is already hold. This already holds. So how to define? So take. So now anyway, starting from here, theta M times OM to theta M. But here, the situation is this. Here, there is a map from M. This we call this map P, and then here, the tautological line bundle is here. Then P star tautological line bundle is, by definition, this is Tm. Yeah. This is not Grothendieck notation. If you use Grothendieck notation, this is P just theta. So this is the this holds, and so this means that the H0 theta is just H0 PM P T star M P T star M 1. Yes. And so let's take a P star, pulling back this homomorphism. Then we get this part can be replaced by this. So P T star M P T star M 1 times this C, this is P star or M, and so this is P O P T star M times P star theta M, but theta M is just this, so we have T P star O P T star M P star. But there is a natural map from P T star M1. Yes, and composite map is nothing but this map. So this is surjective. This is, we call this is beta. Then this is surjective. Yes, by. And now take some point from M. Yes, and take its fiber P inverse X. This is just a P n minus 1, and restrict this homomorphism to restrict this one to Pn minus 1. This is just a fiber of X. Then what happens? Then we have H P T star M O P T star M 1 times. So this should be placed by this to what is this? For example, this one, and this one. So P star P. What is this? P star O P T star M 1 times O. So if you restrict this to this subscheme, it is just this. Yes, this is like this. If you restrict this, then you get here. But this is nothing but H0 Pn. Sorry. This is OM kx times kx p OPN minus 1, and this part can be identified with H0 Pn minus 1, some base change theorem, and OPN minus 1. Yes. So this is if you restrict to this, then you have, so, and this is this, so you have H0 OPN minus 1 OPN minus 1 times this one Pn minus 1. This is she, and this is just P OPN minus 1. Yes. So then this is also surjective. This is also surjective. But if what is this map? This map, you have a global section here. Then if you restrict this global section to Pn minus 1, you get the section here. So this map induced from the homomorphism, linear map of vector spaces from here to here. This homomorphism, this map induced from the linear map between this and this. But if the linear map, so let us consider the following linear map. This is just a restriction map. If this is not surjective, then the composite of this map is not surjective. Yes, because if this is not surjective, then the image of this map is some sort of things. V is some subspace of proper subspace of this vector space, and but if V is proper subspace of this vector space, this cannot generate this. This invertible sheaf, to generate this invertible sheaf, you need at least n independent sections. So if V is not this one is not surjective. So this V should coincide with this. So this is the surjective. But so this is surjective. So this is surjective. If this is surjective, then this is surjective. But what is this? This is nothing but H0 m theta m. But this is just the theta m kx. One can check this. This is just a fiber of this. And this is surjective. So now we have a following surjection. But by using Nakayama's lemma, this implies that x is arbitrary point. So Nakayama's lemma implies that this is surjective. So the automorphism acts on M transitively. But what is this group? In our case, it is checked that Qm is, this is the irregularity is 0. This is checked. So if this holds, this is a linear algebraic group. If Qm is not 0, it has a component of abelian or complex torus component, but if the irregularity is 0, then it is a linear algebraic group. So this is the linear algebraic group. But now M is a flag variety. Then this is actually this is semisimple. So this should be semisimple. Why this is true? Because so now if we put this G, then G acts on M transitively. So M can be written as. So now anyway we put this G, then G acts on M. So transitively, so M can be written as G mod P. If you take some points and take it stabilize a group for such point, then M is isomorphic to G mod P. And M is projective, so compact. This is parabolic. So, but if I want to show that this is semisimple, if G is not semisimple, then you have a non-trivial radical, solvable radical. This is nothing but maximal solvable, maximal normal solvable group. This is the radical. But if the radical exists, but P is parabolic. Parabolic should contain Borel. Borel is a maximal solvable group, not necessarily normal. So Borel, of course, contains this. So now, if the radical exists, then radical should contain in this P. Then radical, you can easily check that radical acts on G mod P trivially. If this holds, then the radical should act trivially on G mod P because of this, the trivial. But G is by definition auto 0M. So this should act on M effectively. So G, by definition, G should acts effectively on G mod P by the definition. So this contradicts, because this is if this is not trivial, then this means that G doesn't act effectively. So this implies that RG is 1. Anyway, this argument says that if M is a projective manifold, homogeneous variety, projective homogeneous variety, then the auto 0M, the neutral component of automorphism group, must be semi-simple. Yes. So this should be semi-simple. Semi-simple Lie group. This is a very important fact. So we have this. Okay, so now let's continue. Yes. Now we have a following theorem. Sorry. Now we put aught 0M. Then we have a following theorem, theorem 1. There exists a commutative diagram X inside C2n plus R and G inside O bar, and this is some isomorphism, and here O is some nilpotent orbit, and G is a Lie algebra of G, and there is a commutative diagram, and moreover, the omega here corresponds to the constant Kirillov form here. This shows that X should be some nilpotent orbit closure, not necessarily nilpotent variety now. The argument is as follows. Proof.
Here, R is uniquely determined for given n through n. The R is uniquely determined.
This R is nothing but uniquely. R is given from the first, because we start from the following situation: 2n plus R. This is the assumption, and so this is the assumption, and this is complete intersection. This is the assumption. Then this is of course given. Then this embedding can be identified with some embedding of nilpotent orbit closure. This is the result of theorem 1, and actually this finally this over is a nilpotent variety. So this R is nothing but a rank of R, rank of G. This is actually this should be the rank of G, but this will be proved in the final part. Anyway, this is just a R. Okay, so how to prove this? The proof is this: if you have now now consider px and take cryptant resolution pi bar, and This is the P star P T star G mod P. Yes, M is just written as in the following form. So G mod P. But you can consider the cotangent bundle, and there is a action of G, natural action of G, because this is a G variety, so the cotangent bundle is a natural G variety. This has a symplectic 2 form, canonical symplectic 2 form, and this action is Hamiltonian action. So you have a moment map for such a G action, but a target space is usually dual. But here, this is a semisimple. So the dual of gay is identified with gay by Killing form, and this is a G equivariant map. So the map is factorized as follows. The image. So, and this is G equivariant map. This is here. This has a natural G action. Here, this has a adjoint action, and so the image of this map is some G variety, and it is a closure of some nilpotent orbit. Take this. So, and this is surjective. So we have the following map. We call this map mu. Yes. So from cotangent bundle to nilpotent orbit closure for some nilpotent orbit closure. Now we projectivize it, because this is also C star equivalent map, so we projectivize it. Then we have a map. We projectivize, and this is Z, and this is P O bar, and this is, of course, it is embedded in the P gay. P gay. And we also have another map. This is our original map, pi bar. And this is the px. And px is sit inside the projectivization of this, p2n plus r minus 1. So we have a map, pi bar and mu bar. We call it the I and j, the natural embedding. And what I want to compare these things. The purpose, and I want to make some isomorphism between among them like that, and such that this commute. But in order to that, we first check that here you have a tautological line bundle, and here you have also tautological line bundle. And then the first one should check that this is the this you have a tautological line bundle here. This should be this is already I erased, but this is already shown. But on the other hand, this part we also have the same things. Px P over 1 is this. Why this is true? Because here you have a symplectic structure here, and you have a symplectic structure here, canonical one, and this is a constant Kirillov symplectic 2 form. But if you pull back the constant Kirillov 2 form, then it coincides with the canonical symplectic 2 form. It means that, and if we projectivize it, symplectic structure gives a contact structure here, symplectic structure gives a contact structure here. So the contact structure is pulled back to the contact structure here. But the contact structure on this variety has a contact line boundary this. So the contact line boundary, the pullback of the contact line boundary should be the contact line boundary of the of the contact structure here. But such a contact structure has this contact line boundary because the contact structure here comes from the canonical one, and the canonical one has such one. So this is the pullback of this boundary is nothing but this. so the pullback is the same. So the final thing is to show that actually this pi bar I both and j and mu bar are morphism determined by the complete linear system. OPT star M1. This is finally we check this. Then so from this these factors say that each map is a map from Z to projective space, but these facts say that each map is a morphism determined by some sublinear system of such a complete linear system, sublinear system.
Excuse me. Here mu is injective or mu? Mu is moment length injective or?
No. Mu is some in okay this one. In this case, this is a resolution. It has a singularities, but almost every part, it is isomorphism. But this is some resolution. This is a smooth variety, and this is a singular variety. So both these maps are morphism determined from the complete linear system. Then it is the same. This is the same map to the same projective space. Then there is some linear transformation such that the image corresponds to here, and you have a map here. So I will omit this part. Anyway, so now we have a following. Now we have this px and this isomorphic as a polarized variety. Because of this is isomorphism. So by using this, one can easily check that you can take cone over this. You take the cone over them, and then you get this map. Taking cone, then you get and the cone over them, you have a map. You get this diagram. If you take cone of them, you have here, and if you have a cone of them, you get a map from here, and it's compatible. So we have a following theorem. So the now remaining task is to show that such over is a nilpotent variety. As I remarked in the first lecture, there are many different nilpotent orbits, and the nilpotent variety is the largest one, and closure of the largest one. So I want to prove. The next step is the following theorem. The theorem 2 says that assume that nilpotent orbit closure, O bar inside K, some semi-simple Lie algebra is a complete intersection, is of complete intersection. And then O bar should be N. This is the final step. This here we are going to use some elementary representation theory. So how does it go on? Yes. So let's take C gay. This is the coordinate ring of the algebraic variety gay. Gay is an affine space. So as an affine space, it has a coordinate ring. So we denote the coordinate ring C gay. Yes, and inside this you have a maxima radial corresponding to the origin. Gay has an origin, and the ideal sheaf of O bar. O bar contains the origin, so M contains I. So this corresponds to O bar. This is the ideal sheaf, and this is maximal sheaf. Yes. And now here, gay has a natural G action, adjoint action, and also C star actions. Yes, G acts on gay, the adjoint action, as an adjoint action, and C star acts just by scalar multiplication. And but these both action preserves O bar. Of course, O bar is O is G orbit, so O bar is preserved by this, and C star also preserved this O bar. And moreover, these two actions are compatible, commutative. So actually, G times C acts on this. And so this coordinate ring has a G times C star action. And of course, these two ideals are also G times C star actions. So we have a following map, I to I, Mi. This is of course surjection, but this is G times C star model. This is a G times C star representation, and I mod Mi is also G times C star representation. This is the map of G module. Yeah, but this is a reductive, linearly reductive groups. So if you have such a surjection, then you can have some sub-representation, sub G times C star module here, such that this is isomorphic. So, and now we take F1 to FR here, such that these are elements of M, such that Fi are homogeneous, and the image here a basis of I mod Mi as a C vector space. This is a finite dimensional C vector space. So okay, then this is generated by F1 bar to FR, but by using a graded version of Nakayama's lemma, if F1 to FR generates such things, then it generates I. So I is generated by F1 from FR as an ideal. So, of course, so then over is the common zeros of the things. And we have a following map from G to M star in the case by using this F1 to FR. This is the, if you take X, then you have here M has a basis F1 to FR. This is a finite vector space of dimension R, and this is a basis. These are bases of M. So this is the Fi to, and this is the map from M to C. So each Fi we correspond Fix. So we have a following map. The I run through. And this is actually G equivariant map, the morphism of algebraic variety. And we call this F. And then F inverse 0, 0 is just origin, is nothing but O bar. And we can check that this is a flat surjective map. So we have a following fibration and C-star equivariant. These are both vector space, but this is not a linear map. This is a affine space and affine space. So this is the map of algebraic varieties and the G equivariant. G acts on G as a joint action, and M star, M is this module, so this is the G module, and M star is naturally dual of it, has a G module structure. So the idea is the following. Anyway, this is not related with the complete intersection. For any such situation, not this, for any such situation, you can construct it. But here you have, if the complete intersection, then you have flat surjective. But except this, you have such a situation. But the point is that if it is complete intersection, this R is small, because usually we need many defining equations. If it is not complete intersection, then we need many equations to define this. But if it is complete intersection, it is the minimal one. So the complete intersection case, this has a very small dimension, but in usual case, it is larger. So this is small if this is complete intersection. This is the point. If this is complete intersection, this is small. But the fact is this. But there are very few irreducible G representation of small dimension in general. If you have a G is the semisimple Lie group, but if the so if this dimension is very small, sorry, this is of course non-trivial. So M star is small. It's small, then M star is a direct sum. So there are few irreducible G representation, but M star is very small. Dimension of M star is very small. It should be the direct sum of trivial representation. So direct sum of trivial G representations. So if such things holds, then this is trivial, so G acts on trivial. So these Fy are invariant polynomials. So if this F1 to Fr are all G adjoint invariant polynomial on G. Yeah. So G acts on G adjointly. So for such action, this is invariant. But O bar is common zeros of such things. But on the other hand, N, what is N? N is a nilpotent variety. Nilpotent variety is actually the common zero. It's just a common zeros of all G invariant adjoint G, all G invariant polynomials. If you take all G invariant polynomials, then the N is nothing but the common zeros of such things. So then O bar is a common zeros of some G invariant polynomials. But on the other hand, N is the common zeros of all G invariant polynomials. Then O bar should be bigger than N. Yes? But N is the biggest one, so this implies that O bar is N. This is the idea. Yeah, so finally I will explain this in the exceptional case. Now, for example, dimension M star is R. Yes, by definition, this is R. And dimension of K is 2n plus R, as I said. This is the original embedding. X is embedded in the affine space of 2n plus R dimensions. But we have a following inequality. This is n plus R, but AI is not less than 2. So we have a following equality, and this implies that the R is this, and then this is the 3R. We replace n by R, and this 2R. So dimension M star is, we have this. But for example, if K is semisimple, exceptional type, for example, G2, F4, E6, E7, E8, any of them, then there are no non-trivial G irreducible G representation of dimension this. So there are no non-trivial irreducible representation of satisfying this inequality. So this M star should be the direct sum of the trivial representation. Then we get the following situation, and we have this. But other cases, not the exception type, this is not true. So we need some other argument, but I cannot say any more about this. So thank you very much. I will stop here, sorry.